They are even more. They're even more fun. I'm less nervous. I'm more normal Frank, less Tiger Tutor Frank.
And awesome. We have harder. We have harder exam. Like I said, I am not good with scripts. Okay, harder exam level problems and cyclical pi system plus cyclical pi systems. All right, we got harder level exam problems and cyclical pi systems.
Hello, I'm Frank, and this is
Jason,
and that is
Carolyn.
Yeah, and I'm the founder and lead tutor of Orgo Made Easy, which is a tutoring service and YouTube channel. I've tutored students from over 40 plus universities, including Boston University, Boston College, Harvard, Johns Hopkins, NYU, UCSD, and a whole bunch of others. And oh yeah, can't forget Maryland College Park, as well as overseas at Queensland University of Tech in Australia. And then Jason's actually worked with some other peeps too, overseas too.
I have, yeah. So a lot of the places Frank talked about, I've also done as well. When I first got into tutoring, I've been doing this now for a very long time, 24 years. And on that journey, I started tutoring people actually in Indonesia. And I obviously don't speak the language. So what I had to wind up doing was they would send me something. I would throw it on Google Translate it, throw it back to them, and ultimately try to do the tutoring sessions. And obviously you can imagine that's not very effective. So I decided to bring it back home to the United States where I know and understand the language. And I've just been basically tutoring all around the United States, same places as Frank.
Yep, exactly. But we realized that we can only help so many students through tutoring, and a lot of students can't afford tutoring. So the goal of Orgo Made Easy, this channel and this podcast series, is to show everyone, regardless of where you are in the world, what your financial situation is, how fun, easy, and interesting Orgo can be. All right?
Yes.
So if you like our stuff and you want to help support us, please consider becoming a patron for us. Patron of us? Patron? Becoming a patron on... Yeah, becoming a patron on patreon.com. Link will be below. Anyways, so we also offer tutoring for Orgo, Physics, Biochem. For more info, check out our website, orgomadeeasy.org. Link below as well. So anyways, let's get started then. Also, BT Dubs Jason's actually the OK Whisperer.
Yeah.
Quiet. Link below to Jason's alter identity somewhere. All right.
Yeah, that's right.
Okay, so welcome to our very first Orgo Made Easy podcast. Each week we'll be covering a scary topic and showing you guys how easy it actually is. For our first episode, we're covering every Orgo student's favorite topic, orbitals and hybridization. So the nightmare...
Wait, what? That's the first topic?
Yeah. It's the nightmare from Gen Chem that you thought you escaped, but it's back. All right.
Boom.
So for this topic, usually you'll be asked to assign the hybridization of an atom in a molecule, or they'll ask you to draw out all the molecular orbitals for the atoms on the molecule. Jason and I will show you how we think about orbitals and hybridization, and we're going to go through an alkane, alkene, alkyne, a conjugated alkene, allene. What else, Jason? What else do we have?
What? Jeez, I see you went through a lot of like benzene. It was like benzene, benzyne, align. Benzene, azide, diazomethane. Are we gonna do that one?
Mm-hmm. Yeah.
Okay, good.
Methane, yeah.
Imidazole, furan, pyridine.
So be sure to check out both part 1, this video, and part 2 of this podcast, which will have all that good stuff, exam level questions, and then you can ace your first exam. Easy peasy. And if you're watching this video before you even took Orgo, your lecture will be a breeze. Okay, so for our first functional group, an alkane, that's basically just single bonded carbons, no pi bonds, aka no double or triple bonds. We chose a nice, simple 2-carbon ethane molecule. First off, question, is the hybridization of this carbon Sp3, Sp2, or Sp? So my trick usually is Sp3 minus the max number of pi bonds that the atom can make. So Jason, what's the max number of pi bonds that this carbon atom can make?
Carbon or hydrogen?
Carbon.
That structure doesn't have any pi bonds. I don't see any.
Yes, exactly. Yeah.
Oh, I got it right.
Yeah, you got it.
I was so nervous.
Yeah, and it's got no lone pairs, so you can't even resonate to create any pi bonds.
Yeah.
So yeah, it is just then, if you use my equation, it would just be Sp3. Yeah, and then also hydrogen, well, they can't hybridize. So you can't ever assign hybridization to hydrogens.
Yeah,
right?
They're basically just an s orbital. Yeah.
Okay, so to understand what the heck sp3 is and like orbital stuff, we need to go back to Gem Chem a teeny little bit. We have to go back to this thing where you have like 2s orbital down here, and then you have a 2p orbital, and then another one, and then another one. That doesn't say 2p. Yeah, another one.
Frank, what happened to the 1s?
Yes, good question. So the 1s is the inner shell, and it's not involved in bonding, so we don't even really care about that. Or me and Jason don't really care about that when we do.
I don't care about it.
Yeah, exactly. And in fact, me and Jason, we just leave out the 2 as well.
Yeah, make it easy.
Too, right? Yeah. So it's just essentially your carbon has 4 arms that can hold on to electrons, the s orbital, p, and p, and these p's are actually in 3 different orientations that you may or may not have seen before. What are the 3 orientations, Jason?
Oof, man, you're asking me a lot of hard questions today, Frank. I think it's X, Y, and Z.
Yeah. Did you read that?
I knew that one. What?
Did you read it from the board?
Maybe.
Yeah.
Don't give all my secrets away.
So s orbital circular.
Is that an apple?
It's a circle. It's a perfect circle. Got it. Yeah. Also, that is not a X. Okay. So your px orbital will look like this. It has more of an hourglass shape. And that is another py X. All right, so your py is going to be vertical like this. And then your pz, it's going to be hard to draw. But I'm going to bold this first part here. It's like that. And then you're going to dash that there. It's like what's happening back there. So it's coming in and out. Yeah.
Here we go. And for context here, we can do this.
Yes.
There we go. Bam.
Yeah. Uh-huh. You want to drop it?
And you said this is, yep, exactly. So this one's X, this one's Y, and Shazam, that's Z.
Exactly. So imagine if I have 4 orbitals, what it is you got the X arms going out to the sides, Y up here, and then Z is front and back, poking you, stabbing the mirror. Yeah. Okay, and then the s orbital is just circular and kind of sitting in the middle. It's going to be lower in energy, hence why it's lower here, because it's more stable. And it's more stable because it's closer to the nucleus of the carbon, which is where the protons are. So electrons in that orbital, in that s orbital, can be held more tightly, and there's less chance of them flying out and doing crazy stuff. All right, and then for XYZ, you'll probably see your professors shade in one of the lobes. So that'll look a little more similar to what you see in class. And yeah, they are higher in energy because see how they kind of have that hourglass shape? Well, pretend like the nucleus of the carbon's right there, and there. So electrons are able to travel further away from the nucleus, and hence electrons in that orbital are less stable and less tame. And so they're going to be higher up in energy. So anyways, yeah, that's what orbitals are. That's what your 2s, 2px, 2py, 2pz. And now going back to our carbon, why is this all related? Well, it turns out if you have 2 carbon atoms and they get close to each other, they will hybridize each carbon will hybridize their s orbital with their 3p orbitals. Because if you merge them together, Jason, I'm going to erase your little axes there. Okay, if you merge them together, it turns out that you can produce, there's 4 orbitals going in. So you're going to pump out 4 orbitals. And it turns out you're going to pump out 4 orbitals that are lower energy than your p, x, y, z orbitals, but higher energy than your s orbital. Okay. And since they're composed of 3p orbitals and 1 s orbital, that's where the term sp3 comes from. Cool.
What do they look like?
Concerns? Yes. Do you want to draw them, Jason?
Yeah, sure. But yeah, when these things come together, you can imagine it's not a perfect fit, because if we looked at, like, let me use my finger here. If we looked at, for example, this right here, matching with the s orbital here, only half of it, if we lined up, would match up with the purple, and 1/2 would be a mismatch. So we get this really cool thing that happens where one of the lobes is bigger, and then the other side is going to be a little bit smaller because it's not as good of a match. It's pretty tiny.
Yeah, and then because they're hybridized from 3p orbitals, it should have more of an hourglass look to it. So actually, I'm going to have Jason tweak it a little bit, because his looks pretty, yours looks pretty S-y. Let's make it a little more P.
You want to make this one big? Okay.
You can make that a little bit bigger. Yeah. No? Okay.
How about that?
Yeah, that looks great. Yeah. and we'll just mentally shrink it down a little bit. But yeah, essentially that's what an sp3 orbital looks like. Pretty p-ish, but it's got like a fatter lobe on one end due to the s characteristic. Yeah, I like that. Awesome. Great. So you're going to have 4 of these, and what's going to happen is, if you imagine you are a carbon, and these orbitals have electrons, you don't want the electrons too close to each other, otherwise they're going to repel each other, and it's like 4 kids, they're going to have a fight. Jason would know.
Oh yes.
Yeah. So what the carbon atom is going to do is it's going to space them out as maximally as possible, and that's probably where you hear about the term tetrahedral. So let's go over, I'll go down here on
okay.
Here's our carbon atom. Let's see. Actually, Jason, do you want to try drawing it? The tetrahedral positions of the 4.
Oh, with some dashes and wedges and stuff? Oh yeah, I can do that.
Yeah.
Absolutely.
Yeah.
Let me see what we got here. We got all right. So we're gonna have, do you want me to do this tiny lobes or just the big lobes?
Yeah, so for context, guys, we're just gonna show you the big lobes because
Cool.
It's kind of hard to fit in the tail ends. So yeah, Jason's gonna pop an sp3 orbital going straight up north.
We got that one. We're gonna have one that's gonna go Shazam on this side over here.
Awesome, still doing there.
This one in, and then this one, I'll exaggerate this one. So this one's gonna be like boom, like this. Yeah,
it's coming out at you basically. I know it looks like it's going to the side, but it's kind of going up the side, but also like at your face.
And that one's gonna be teeny tiny.
Yeah, exactly. And keep in mind that all 4 of these sp3 orbitals do indeed have a tail, but we can't show you because otherwise it's going to be a hot mess. All right.
So it's kind of like a tripod is the way that looks like.
Yeah. And then what they probably see in class is a carbon tetrahedral that looks like this.
Mm-hmm. Exactly.
That might look a little more familiar, but just know that in reality, in terms of orbitals, this is what's happening. And there are electrons in each of these orbitals. Yeah. Yeah. And then you probably heard of 109.5. Well, this is where we get that magical number from. That's the bond angle between each of the sp3 orbitals. All right.
Why is it 109.5 and not 90?
That's a great question. Why is it not 90? It's because if you do 90, that means you're doing like north, south, west, east. So you're on like a flat plane, and 90, that's the maximum you can do. But then if you think about it, that's just in 2D. There's so much space in front of you and behind you. So you might as well, shift your, your firstborn a little bit more forward and shift your, other born a little bit back. I'm not a parent, so don't know. Yeah. Yeah. So that's why it's better for it to be tetrahedral, take advantage of the 3D world we're in versus the 2D, 90-degree world. Yeah, that's something. Okay, and then so when your 2 carbon-carbon atoms come together, basically you have this going on the left carbon and this going on the right carbon as well, and they join and meet, and then they form your ethane molecule. Yeah, so in reality, what's happening is, thanks to Jason, who used ChemDraw, created these beautiful figures over here.
You're welcome.
Should tip Jason on Patreon if you like them. Yeah, so what's happening is these are your 4 sp3 orbitals over here, and these circles over here, Jason, why are they circular? Why are they not hourglass shaped?
Yeah, the cool thing about that is hydrogen doesn't hybridize, so it's basically just a big S orbital. So it's basically just a circle that's going to onto one of the hybridized orbitals.
Yeah, exactly. And if you're wondering why hydrogen doesn't hybridize, it's only got 1 electron. Yeah. In its 1s orbital. It's all got
no bueno.
Doesn't have 4 arms. Yep, exactly. So that's what's happening. That's what the hydrogens are, and this is what you should draw if you're asked to draw a molecular orbital diagram.
What's the one on the right, Frank? What's that?
This is, what do we do? Oh yeah, we wanted to show you guys that there is indeed the tail end of your sp3 orbital here, but we can't fit it in. So just wanted to show you what's happening. Okay. Alrighty. Any questions? Let us know down below in the comments. And if you need more help, reach out to us. We can set up a tutoring session with you. Oh, we should probably mention this, but the type of bonds right here, that's a sigma bond. This is a sigma bond. These are all sigma bonds. Okay, they're not pi bonds, which we'll see soon enough in the next example. And then you might be asked on your exam to label what type of sigma bond it is. So for this sigma bond right here, what you would do is you would label it a CsP3 sigma bond. This bond right here this would be a Sp3 H1s sigma bond going on over there. Okay. Yeah, I remember Providence College tends to do that. So if you're at Providence, PC, keep your eyes on that. Okay, cool. So I think we're all set here then, Jason. Yeah?
Okay, yeah, I think it's good.
All right, so to wrap up, sigma bonds are basically when you have two orbitals pointing at each other and they are touching and they form a nice stable bond. We're going to see in the next example for ethene what a pi bond is. All right, and also what the heck Sp2 and Sp is, where they come from. So for ethene, the way it works is, let's do it, Jason. So question, what's the hybridization of this carbon atom over here?
I have three choices, right?
Yes.
1, 2, or 3. I'm going to say, I'm putting it out there. I'm going to say Sp2.
Yeah. Sp2. So did you use my equation?
I did. That's the only way I know
did?
how to do it.
Awesome. Okay. So the max number of pi bonds that the carbon can make was how many?
I was just kidding. I actually didn't use your equation.
I know.
The max number of pi bonds, I'm going to say 1.
Yeah, exactly. Yeah, this one right there.
Exactly that one.
Yeah. Yeah, so the way that me and Jason are kind of visualizing is that, we know that basically every time you have a double bond, one bond is a sigma bond, like we saw earlier with ethane. And this second bond, the top one, is the pi bond. All right. And then we love pi bonds and like problems that are like Sp2 and Sp hybridized, because then we're dealing with p orbitals and they're really cool to look at. Ethene, with my equation, Jason already established that it's Sp2, Sp3 minus the 1 pi bond. Boom. It doesn't have any lone pairs, so it can't resonate. So we don't need to worry about any additional secretive pi bonds showing up. And then hydrogen, like we talked about before, is just can't hybridize. So the next part is your prof will probably ask you to draw the molecular orbitals out for your atom. So this carbon's Sp2, and what's happening is that because it has a pi bond, the way a pi bond works is that unlike sigma bonds, which are when two orbitals are touching and pointing at each other, it's set up by two parallel p orbitals. More of like a long.
Frank, can it be a bond if they're not touching?
Yes, it's like a long distance relationship. That's the way you can think about it.
That's good.
Two parallel orbitals. Yeah, you have a p orbital on this carbon and p orbital on this carbon, and that's what's causing the pi bond setup. So this is our pi bond, and then this is our sigma bond that we've included in here. A lot of times people think that when I do this, I'm referring to like both bonds. That's not the case. This entire thing is just that top pi bond right there. And then the sigma bond is that bottom sigma bond right there. Okay, just to clarify that. All right, Jason. And then I saw that we did some dashing and wedging here. What's happening there? Why did we do that?
Yeah, so on this one, let me get my finger. All right. So on this right here, we draw this, like Frank said before, like obviously we don't live in a 2D world, we live in a 3D world. So this right here, we draw this is flat. But if we were to draw the p orbitals, they would literally be coming right off there and hitting us in the eyes or the face. So what we try to do with my hand here is we're trying to take the molecule and slightly rotate it like this or like this. So we're actually, the dashes are putting the hydrogens behind our computer screen. The wedges are coming through our computer screen, and it allows us to put our p orbitals up so we can see them.
Yeah, exactly. So I'll bring back that little diagram earlier that I did, px, py, pz. Typically, Jason and I, we both default to using the py orbitals for the first pi bond, because I think it's the easiest to set up. So in order to set up this pi bond, we have to sacrifice a py orbital and basically drag it down here from this left carbon. And then the right carbon has the same setup, px, py, pz, s, and we drag it down over here. So the reason why pi bonds are so linked to the hybridization of an atom is that if you sacrifice a p orbital, then all that's left is what, Jason? How many p orbitals do you have remaining if you knock off a py?
Square root of 7, 2.
Exactly. Square root of 7. Yeah. So you have 3 orbitals going in, 3 coming out, and instead of sp3, they're going to be what, Jason?
They are going to be sp2. What, Frank? What happens to the other p? Is that other p orbital on the same level, energy level? Where does that go?
This one, it just I think it just stays on the same level, or I guess
so I think it's higher. It's higher, right?
This one, the py.
Yeah.
Yeah.
I think it stays up on the same level, right? Yeah.
Yeah. I think we could just transfer it up here. like that. Yeah.
Yeah.
And yeah, so these three hybridize, boom, 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 3 sp2 orbitals. And just like before, they're responsible for the sigma bonding network, which is what's happening over here. And then you still have your hydrogens, and that's what's happening over here. And voila, that's what's happening on the molecular orbital level for ethene. Okay, same thing. Any questions? Fire them down below. All right, so then next coming up is ethine, which is an alkyne. So question, what's the hybridization of this carbon atom?
All right, so I'm going to use your formula here. Okay, so
yeah,
sp3, the square root of 7 divided by 2. Okay, so that's going to be sp.
Sp, yeah, because the max number of pi bonds is
dos.
2. Yeah, awesome. Also, yeah, we know there's no resonance. You don't need to worry about any sneaky additional pi bonds. So let's reveal what's behind the black box then. And then I'll do, yeah, there we go. Here we go.
Ah, there it is. Yes. I
all
see
right. So what in the world is happening here, Jason? What are all these diagrams we have?
Cow. My head just, yeah, this is super, super weird. But as Frank talked about here, what we have is we have our sigma bond, but we also have these pi bonds. So what we're trying to do here is if we look at this right here, let's start with this one. So if we look at this one right here, we can see that this would be one set of the p orbitals. So for example, that diagram Frank did where we had the X, the Y, and then the Z. This, for example, would be, I can't remember which one we did, maybe Y. Can't remember which letter of the alphabet it was, but
these
would be the Y. Yeah.
Yeah.
Is that Y?
Yeah.
Okay.
Yep.
All right. So we've got our Y p orbitals up here. So that would be like, let's say the top one, the top line of the alkyne. This one right here.
So what you guys probably would see in class or in your textbooks, your Z would look like this. But what Jason did, which I really, really like, is that in reality, it looks more like this. They look like eyeballs looking at you instead.
Yeah, so if we look at the red one and then either one of the blue ones, particularly this one all the way on the right, we can see that we have one of the pi orbitals here. We have the other pi orbital here. So that takes up 2 of our lines, the top and the bottom of the alkyne. But then this middle one right here, which we've seen before, are going to actually have our hybridized orbitals in the middle right there. So you can kind of see what we've tried to do on this one over here. The bottom one too here is this one here is with the hydrogens, is tried to show you what everything would look like if we had the p orbitals, the top and the bottom, and all of the bonds as well. A lot.
Yep. I'm just going to go back to my little go-to setup, px, py, pz one more time. Because this alkyne has 2 pi bonds, we're sacrificing both the py and the pz orbital. So bye. I just kind of mentally forget them in terms of for hybridization. So then all that's left is 1 p going in and 1 s going in. So you're pumping out 2 sp orbitals. That's it. So that's why the carbon has to be sp hybridized then. It's easy as that.
Yeah, this was pretty easy. It's basically a straight line, 180 degrees, and done.
Yeah. So py orbital, right? Actually, I'll just go ahead and label it. Py orbitals right there. Pz orbitals. You have 1 electron here, 1 electron here. It's circulating in this pi system. 1 electron here, 1 electron here, circulating in that pi system. And that's where we get this setup. I'm going to go ahead and same thing. Electron, 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 zoop. Over here is what it really looks like, basically. Yeah, the Z's are pointing right at your face. If you guys guess what orbitals these are, here and here. If you said sp, you are correct. Okay, so that's sp, and that's a carbon sp sigma bond. And this over here is a carbon sp H1s sigma bond. Alrighty, so that's part 1A. Be sure to check out part 1B and 1C. They're even more fun. I'm less nervous. I'm more normal Frank, less Tiger Tutor Frank.
We got harder level exam problems and cyclical pi systems.
So be sure to like this video down there, subscribe, and hit the bell button because bells need to be rung. You can help support us by buying us a latte or boba on Patreon. On the higher tiers, you can submit questions for this podcast. You'll get a backstage behind the scenes pass with us. And this is where you talk about your supportive soccer dad tutoring style.
Awesome. And if you guys like my supportive soccer dad's tutoring style, you can go ahead and click below and sign up for my Kajabi OChem 1 course. Or
tutoring through Orgo Made Easy, link below. Also, special thanks to one of our earliest supporters. I think he was like our first patron on Patreon way back in 2016. something. This is Boston University's genetics professor, Chip Salenza. He was also the professor who I did research for in his lab way back in like 2013. So thanks, Chip. And as always, Chip, make sure you hit the pause and try out the problems.
I don't need no stinking pause button. Nah.